Okay, so hi everyone, welcome back to my YouTube channel. My name is Jande Nyanugui. So in the last video, we saw the paper attention is all you need, which introduced transform architecture. Today we're going to look at vision transformers from the paper and images of 16 by 16 words, transformers for image recognition at scale by Dosovitsky et al. So we start looking at the abstract and then we'll slowly diving deep into the main architecture. Why the transform architecture has become the de facto standard for natural language processing tasks, its application to computer vision remain limited. In vision, attention is either applied in conjunction with convolutional networks or used to replace certain components of convolutional networks while keeping their overall structure in place. We showed that this reliance on CNNs is not necessary and a pure transformer applied directly to sequence of image patch can perform very well on image classification tasks. When pre-trained on large amount of data and transferred to multiple mid-size or small image recognition benchmark like ImageNet, CIFAR 100, and VTAP, Vision Transformer or ViT attains excellent results compared to state-of-the-art convolutional network while requiring substantially fewer computational resources to train. So the outline of this video is like this. So we'll start with the motivation for ViT and then I'll look at its main architecture and then look at fine-tuning ViT, then training ViT, then we compare it to ResNet and then we look at ViT representation and then look at self-supervision and we see the main difference between vision transformers and CNNs and then we see some popular ViT implementation. And then we close with some recent follow-up works like scaling ViT, better train ViT, how to train ViT, and scaling ViT to 22 billion parameters. So Andreas mentioned, all image and graph we use are taken from the paper. So let's start with the motivation for vision transformer. Due to the transform architecture, which has extreme scalability and efficiency, NLP has been successful. Like the aim has always been to train or to pre-train a transformer model on right datasets, which contain all Wikipedia news and books and codes, and then fine-tune on downstream tasks. So NLP has been successful due to three main ingredients, which happen to be all available at the same time. So one is large dataset, two is efficient models like transformer obviously, and compute. So transformer seems to be the main engine of all. And the question is, can we apply the same transformer to image recognition tasks? So before the emergence of vision transformer architecture, most works attempted to apply transformer to computer vision in three main ways. The first way was to replace all convolutional operation with local attention. The second option was to combine convolution and attention. And the third option is to apply transformer to image pixels directly. We're going to look at each of these three options. So let's look at the first option, replacing all convolutional operation with local self-attention layer. This was introduced in the paper Standalone Self-Attention in Vision Models in 2019. So normally in local convolution, we take the output for each local window is the inner product of convolutional kernel and local window or receptive fit. So the local self-attention which introduced in this paper is that so we take you know the standards self-attention. So this paper tweaks local conversion into local self-attention layer by treating the center pixel as the query and treating all other pixels and keys and values, and then we perform self-attention within this local window and then we get the output basically. So this is pretty straightforward, but there is a problem. So local self-attention is not scalable and hard to implement, given that you are doing this for every window, and this is too much. So this is not compute efficient, even if attention is computed in local windows. So another popular ways of using transformer in vision is combining convolution of attention. So this was demonstrated in the paper Data, which combined convolution attention for object detection. And this was very successful because even the data is one of the most popular papers in the computer vision. So the idea of data was to run 2D visual features of image with convolutional backbone like resonate, feed the features to a transformer and predict the box and object class. So CNN plus tension seems to work right when done right. And as we said, data is one of the remarkable papers in the computer vision. So a third option of applying a transformer to vision is applying a transformer directly to pixels. So the idea here is to treat a raw image as a sequence of pixels, just as a sentence is a sequence of words or character in NLP. And then we resize the image to a raw resolution since attention is computed to every pixel, and that's very expensive if I'm doing that on high resolution image. And after that, we flatten the pixels and then we feed them to a transformer to predict the next pixel progressively, or with masked pixel prediction I can build. This was done in the paper Generative Pre-training from Pixel in 2020 by Chen et al. So this is also not efficient because if you're applying transformer in each pixel, then it's super expensive as each pixel has to attend to each pixel. So the main goal of ViT authors were to transfer NLP pre-training success to computer vision and to remove the need of convolution. Given the previous works, the biggest breakthrough was honestly not applying transformer to image. It was essentially dividing image into a sequence of patch and feeding those patch to standard transformer encoder. And this is true. Like as we saw, some people try to apply transformer to a sequence of pixels, and some people try to apply transformer into local windows instead of doing convolution. So, like the main ingredient for ViT was to basically treat image as a sequence of patch and then feed those patch to the whole transformer encoder as it is. The same transformer used in NLP basically. So now let's look at the transformer architecture. So the first step in the transformer architecture is patchification. So where we take an input image and then we divide it into non-overlapping patch and then we flatten them into a sequence of 1D patch. The second step is to linearly project or patch to the dimension of the model. This D is a hyperparameter that you can tune. And the third step is to apply position embedding to patch. The fourth thing is to then feed the patch to a normal transformer encoder. So this transformer encoder is pretty much the same as the same encoder in NLP, with the exception of Rhiannon that comes before attention and MLP. And after that, you add a classification head to perform image classification. So now we look at the training of transformer. So vision transformer was pre-trained on 3 datasets of varying size and scale. So the first dataset is ImageNet 1K, which has a 1.3 million image and 1K class. The second dataset is ImageNet 21K, which has 14 million images in 21K class. And the third dataset, which is not public, is JFT, which contain 303 million images and 18K classes. So ImageNet 1K and ImageNet 21K were also used during fine-tuning. So our vision transformer was pre-trained with same configuration as ViT. So they trained three transformers of different size, ViT base, ViT right, and ViT which. What you see here is their configuration. So the layers, when you say layers, we mean the number of transformer encoder, height and size, the dimension of the model. For ViT base, the height and size was 768, and for ViT large it was 1024, and for ViT huge that was 1280. So MLP size is the number of neuron and MLP layers. You can see the different MLP sizes in all three variations of ViT, and heads are the number of attention layers in multi-head attention. And params is the total number of parameters of the whole model. So something to add there is that ViT is isotropic architecture, which means that the same resolution is maintained across the whole network. So let's look at fine-tuning vision transformer. So ViT is pre-trained on right dataset and fine-tuned on small downstream dataset. So like bits during fine-tuning, the pre-trained classification head is removed and it's replaced with zero initialized decay. This is the height and size, and K is its number of downstream classes. So for example, for ViT base, D would be 768, and then K, maybe let's say for CIFAR 100, K would be like 100 classes basically. So, and for fine-tuning, the datasets are ImageNet 1K and 21K, CIFAR 10, CIFAR 100, Oxford 3 pets, Oxford Flowers 102, and VTAP, which combine natural, specialized, and structured tasks. So one of the insights from this paper was that fine-tuning at high resolution, which is 384 by 384, provided better results. And so here the thing was that, like in the pre-training, ViT was pre-trained on image of 224 by 224 resolution, but then during fine-tuning, they fine-tuned that high resolution, and then they got better results than fine-tuning on the same resolution. So at a fixed batch size, high resolution result in large input sequence length, as we saw in the formula of effective input length N. So you can fine-tune ViT at any higher resolution since it can handle arbitrary patch length, but it might affect pre-trained embeddings. You can read the paper more about the fine-tuning details, but this is the main important thing to know for fine-tuning ViT. So now let's look at vision transformer with CNN, where we are looking at ResNet here. So we're going to compare vision transformer and sorter on two different things. The first thing was the ImageNet top 1 accuracy by the pre-training dataset. So one of the first thing is that on small pre-training datasets like ImageNet 1K, like ResNet perform better than ViT due to that CNN has a spatial inductive bias which compensates for smaller datasets. I think this is not established explanation yet, but one of the, like currently, we believe that CNN perform better for small data set than ViT because of their inductive bias, but this is not really established explanation. So on medium pre-training datasets, like ImageNet 21K, ViT and ResNet performance are almost similar, although ViT performs slightly better. And on large pre-trained datasets like JFT, large ViT outperform ResNet and show no sign of plateau. So you can basically keep training it. So also rates, as we said, we are comparing Vision Transformer and CNN in many ways. So here we compare the transfer accuracy and the pre-training computes in exaflops. So one flop is one multiply add per second, and flop usually it really means like floating point operation per second. So on the pre-training compute, ViT query outperform ResNet on performance with compute trade-off, as we can see on this graph. And also, as you can see, ViT use approximately 2 to 4x compute to achieve the same transfer accuracy. This is the average of all downstream datasets, by the way. And hybrid model, which is a combination of CNN and ViT, slightly outperform ViT on small compute, as you can see this orange graph, but it vanished on large compute bucket. You can see that as you increase compute, hybrid model start to vanish, while ViT has no sign of plateau. And like I said, ViT shows extreme scaling behavior. Its performance doesn't seem to saturate for increased compute. So now let's look at the ViT representation. Vision Transformer shows remarkable performance when trained on massive dataset. So, but the question is, how does it process image internally? So what you see here below is the RGB embedding filters or the first 28 principal components. So when you visualize the embeddings of the flattened patch, you see that the face of ViT, which is the linear projection, learns the low-level features such as edge and blobs of the image, and this is very much like convolution networks in the face layers. Also, we can also look at the position embedding similarity. So Vision Transformer learns to encode the distance within the image in similarity of positional embeddings. So as you can see, the patch which are close to each other are likely to have similar position embeddings, and the row column structure is also maintained for all patches. So the patch in the same row and column have almost similar embeddings. Also, another important thing to look at here is the mean attention distance per network depth. So as you saw on the graph, each dots represent the mean attention distance, which is pretty much similar to the selective feed in convolutional networks across image for every head and layer. So mean attention distance, as you can see, increases with layers, but some heads attend to most of the image in ear layers. So attention can attend to the whole image with fewer layers than CNN. As the conclusion for this. But it's more clear when you are looking at the global level than internal representation. So you can see that like when you try to look at the part that the model is focusing on, you see that like ViT tries to attend to the meaningful part of the image. Like for a plane, for example, you see that the model is able to know that this whole thing of background doesn't really improve the performance, and what's really important for this image is the plane. And this is also shown in another image as well. So the representation by ViT is more explored was more explored in recent works, and I think there's a lot of ongoing research about how like vision transformer works. So I've added some few works if you're interested in this area of research. So like how do vision transformer work? Do vision transformer see like convolutional network? What do vision transformers run? A visual exploration and intriguing properties of vision transform. I think this is a really great paper that you can read if you're interested in the ViT representation. Now let's look at self-supervision or training ViT with self-supervised learning. So as we saw, most of transformer success in NLP is the result of large-scale self-supervised pre-training, where a transformer is trained on massive unreliable data from the web. There are a lot of unreliable data on the web. So if you can find a ways to train on those unreliable data, I think that's huge success, and that's why NLP has been very successful in recent days. So using masked word prediction technique that were used in BERT, where they randomly masked words in input sentence, ViT designers also tried the same technique, where they masked 50% of the patch. This is called masked patch prediction, but they achieved less performance than supervised pre-training. So I think the accuracy here was 79.9 accuracy on ImageNet with self-supervision, while supervised pre-training achieved roughly 85 accuracy. So there's a huge difference between the two. So now let's look at the comparison between vision transformer and component. This is overall comparison. So which is better? Like of like which is better among the two? So ViT and component can both run useful representation, but they are fundamentally different. So ViT is isotropic architecture, which means that it maintains the same resolution and channels across all blocks. And components are hierarchical, so resolution decreases with depth, and the channel usually increases with depth as well. So vision transformers are one of the greatest and recent markup paper in visual representation learning. They have outperformed components on various benchmarks, but it's still an open research question whether they will replace components or not. So, for example, ViT was once sought on popular computer vision benchmarks such as ImageNet and CFL 100. At the time of making the slide for this video, VITG was a SOTA on CFR 100, but you can look at the paper of code for recent SOTA on computer vision benchmark. So yeah, VIT and component, which is better? So I write this tweet from Jan Rikon, which said that, am I going to argue that component or convolution is all you need? No, my favorite architecture is later like component or components for the first layers, then something more memory based and permutational invariant like transformer block for object based reasoning on top. We saw that in previous slides. So I also like this comment from Justin Johnson, one of the computer vision expert I know. So vision transformers are an evolution, not revolution. We can still fundamentally resolve the same problem as with CNN. The main benefit is probably speed. Matrix multiply is more hardware friendly than convolution. So ViT with same flops, CNN can train and run much faster. So now let's look at ViT implementation. So, so the original ViT paper was implemented in the repository Vision Transformer, which I added here. and this is in JAX and FRAX, but it also contains other rated models and papers such as NLP Mixer. And another popular implementation is Big Vision. I think Big Vision is a new code base for training ViT and related models and papers. It's maintained by the same team which introduced the paper basically. So also the repository contains a checkpoint and instruction for training and fine-tuning ViT models. This is also in JAX and FRAX. So another popular implementation of ViT is ViT PyTorch by Lucid Brain, a popular guy, a popular transformer guy. So this is the implementation of roughly all popular ViT papers. So you can check it out. It's in the PyTorch. And you can find other implementation on paper of code as well. Like if you search paper or if you go on the page of the paper, you will see that like they have, like you can see like all other popular implementation of the ViT architecture. But I believe the most popular one is the one I just shared. So now let's look at some follow-up works related to ViT. So the first paper, which followed Vision Transformer paper, is called Scaling Vision Transformers. So in this paper, they successfully trained a ViT of 2 billion parameters and achieved 90.45 top one accuracy on ImageNet. So the graph you see here shows the ImageNet fine-tune error rate and the compute, which show TPU V3 core days. So one of the things they found is that the model trained for fewer image. The fewer image means more markers, as you can see here. So the model trained on fewer image, like 30 million, saturate and start improving when trained for longer. You can see that like these models with small dots basically, like when trained for longer, they saturate and they stop improving. You can see here. Another insight was that scaling up compute and model and data together improve representation quality. So if you increase compute and you increase the model, the big model are the one with the red shading. So all these red shaded dots are basically the big models or large models. So if you increase compute and then you use large model and increase data, the big dot, it improves the representation quality. Also, a model, the one with the connected points, I believe, with rated size that's red dots, dataset size that's like huge or big dots, which is 3 billion, and compute achieve the lowest error rate. So yeah, like this was what was said in previous insight as well. Like a model which has the largest size, which is trained on large dataset, and given enough compute, achieve the lowest error rate. And this was consistent across fine-tuning and future training. Another nice graph from this paper is the one which shows the error rates and the model size in gigaflops. So this graph shows that representation quality is bottlenecked by the model size. Again, remember that the size of the model is shown by the color. So blue shading means it's small model, and then red shading means it's large model. And for data sets, small dots or the size of the marker means size of data. So model trained on fewer image are shown by small markers like this. So smaller models, the one in the blue shadings, are not able to benefit from either the largest data or compute. So you can see that all small models, they don't benefit from compute. If you increase compute for small models, it's basically wasting time. But large models, on the other hand, benefit from both. Like large models want you to increase the compute and increase the data at the same time. Another nice graph from this also shows the error rate versus data size in million. So when scaling up the model size, the representation equality is limited by small data sets. So large models benefit from increased data sets, large models, the rate shadings, but smaller models are hurted by that data set. You can see that as you increase the data set, like smaller models, they don't improve, they vanish. But if you increase the data sets, large models, they benefit a lot. Another nice follow-up works is better pen ViT baseline for ImageNet. I think this was a very small paper, maybe like 2 page if I remember. So better pen ViT baseline for ImageNet. I wrote the abstract since it's pretty small. So it's commonly accepted that vision transformer model requires sophisticated regression technique to excel at ImageNet 1K scale data. Surprisingly, we find this is not the case, and the standard data augmentation is sufficient. This note presents a few minor modifications to the original vision transformer vanilla training setting that dramatically improve the performance of brain ViT models. Notably, 90 epoch of training surpass 676 top 1 accuracy in under 7 hours on TPU V38, similar to classic ResNet baseline, and 300 epoch of training reach 80% accuracy in less than 1 day. So I think the key thing here was that simple ViT can basically achieve comparable performance to ResNet by changing a few things. One is using standard data augmentation, using fixed position embedding instead of runnable embeddings, changing batch size from 4006 to 1024, using global average pool instead of extra class token, and using MLP instead of one linear head. You can see on this graph that by making the change, you can actually improve ViT on ImageNet 1K. Another cool paper that followed ViT is how to train your ViT, data augmentation and regression in vision transformer. I also read the abstract for this paper as well. So vision transformer ViT have been shown to attain highly competitive performance for a wide range of vision applications such as image classification, object detection, and semantic image segmentation. In comparison to convolutional networks, the vision transformer weaker inductive bias is generally found to cause an increased reliance on model regression or data augmentation, or GREG for short, when training on small training dataset. We conduct a systematic empirical study in order to better understand the interplay between the amount of the training data, OGREG, model size, and compute budget. As one one result of this study, we find that the combination of increased compute and OGREG can yield models with same performance and more trained on order of magnitude more trained data. So we train ViT models of various size on the public ImageNet 20K dataset, which either match or perform their counterpart trained on larger but not publicly available GFT300M dataset. So the problem with ViT is that like training it require an certain amount of data. If you remember from the original paper, the like attractive results or attractive accuracy were achieved because training it on JFT 300 dataset, which is not public. So the question that this paper started was, what's the interplay between amount of training data, augmentation or regression, or OGREG in short, model size, and the compute bucket? Like, what's the interplay between those four things? Like amount of training data, augmentation and regression, model size, and the compute bucket. So the paper showed that carefully selected amount of regression and data augmentation can actually compensate for ViT need of more training data. So in particular, a good mix of regression and augmentation roughly correspond to a 10x increase in training dataset. So if you are very careful on how you regularize and how you do the augmentation, you basically would never need to train this ViT on right dataset like JFT. So the regression technique used in this paper was weighted decay, stochastic depth, and dropout in fully connected layers. And that augmentation was mix up, and done to augment. So let's look at one really cool graph from this paper, and then we'll try to understand like the interplay between these four things. So for smaller datasets, both regression and data augmentation help. This is what you see, like as augmentation increase, as you go like this, and this is not regression, this is regularization. So for smaller dataset, like imagine it 1K, if you regularize and you do a augmentation, it actually helps. You can see that the best results were achieved where like there's regularization and there's medium to heavy data augmentation. And for medium trash datasets, medium here I mean like 21K. Both regression and data augmentation hurts when training compute is fixed. So for like 30 epoch, for example, you can see that like it's the best results are achieved almost like when you're not regularizing. So like when you're not regularizing and when you're not using heavy data augmentation. So like for medium dataset, like regularization and augmentation like doesn't help that much when your compute is fixed. But for large datasets or medium datasets still, both regression and data augmentation yield better accuracy for increased training compute. So if you change basically the same setup except that you are changing the compute, you're going from 30 epoch to 300 epoch. So both regression and augmentation they help. You can see that the best result were achieved when you are regularizing, like when you're like it's maybe a mix of both, like heavy augmentation and then regularization. So the last follow-up work, which actually introduced recently in 2023, it's not been like maybe even 2 months since these papers are introduced. It's scaling vision transformers to 22 billion parameters. So the scaling of transformers has driven breakthrough capabilities for language models. At present, the largest large language model, LLM, contain upward of 100 billion parameters. So vision transformers or ViT have introduced the same architecture to image and video modeling, but these have not yet been successfully scaled to nearly the same degree. The largest dense ViT contains 4 billion parameters. We present a recipe for highly efficient and stable training of 22 billion parameter ViT or ViT22B and perform a wide variety of experiments on the resulting model. When evaluated on downstream tasks, often with right-weight linear model on frozen features, ViT-22B demonstrates increased performance with scale. We further observe other interesting benefits of scale, including an improved trade-off between fairness and performance, state-of-the-art alignment to human visual perception in terms of shape, texture bias, and improved robustness. ViT-22B demonstrates the potential for LLM-like scaling in vision and provide key step toward getting there. So the main thing here is that like language models or LM or say LLM can be scaled to over 100 billion parameters, but largest ViT up to date was around 4 billion parameters. So it's all the same architecture, it's all the same transformer with a little bit of difference. So why can't ViT models be scaled to more beyond parameters? So this paper basically presented the largest dense ViT, which has like 22 billion parameters, and just show the training recipe for achieving that scale. So ViT 22B is roughly the same original ViT with three main architecture change. So the first change is the parallel layers. So instead of arranging attention and MLP blocks in series, ViT-22B applies them in the parallel. You can see that attention in block and MLP block are parallelized. So they take the same inputs instead of one being next after the other, as it was in the original transformer. Another ingredient for achieving this scale is applying normalization random to queries and keys. So when attention logits are extremely large, attention weight can vanish. So query and key are fed through random before dot product attention to stabilize the training. And the last ingredient is omitting bias term in query key vector projection and random. So following previous novel works like PAM, ViT-22B suppressed bias term in query key and value linear projection, layers and random, but keep them in NLP in and out and attention out. So you can see that they remove the bias term in the query key and value projection, but they keep the bias term in MLP and in attention out. So ViT-22B improve training and hardware stability. It achieved certain several vision benchmark and claimed to be more aligned with human for shape and texture bias and more robust compared to existing models based on ViT. So this is the end of the video. Thank you for your visual attention. I hope to make more videos around popular topic in AI research, computer vision, and large language models, and other hot topic as well. So please subscribe, stay in touch, and if you have any question, please reach out to me either in the comments or Twitter. Thank you for your visual attention.